refer here. So I'm talking about data breaches, starting with an imaginary one, and then a real one. And then I'll talk about the IPv6 RA flood attack, because there's a new one. It came out just about a month ago, which is much more powerful. And it is highly entertaining because it kills the Mac and it kills Windows. There's not too often things that will kill the Mac. So I'm Sam Bowne. I teach at City College, San Francisco here. And so at the beginning of this year, we were in the news for having the worst data breach you could ever imagine. All our machines infected for 10 years. It was on the front page of the San Francisco Chronicle. It went all over the news. It went to other countries. It went all over the place. Anyway, the result, this became a huge sensation and created a lot of problems at the college because everyone was afraid to use their computers. And people tried calling me, and they tried calling the people on the IT team, and nobody knew anything because the CTO had taken it on himself to prove their story in the newspaper without any of us being in the loop. And this is the story, which was also published in great detail in the newspaper. We were infected with viruses, supposedly. That's what they look like. They live on your computer and crawl down the screen and take pictures of your data and send it to the Russian business network. And teachers like me are ignoring obvious symptoms of this and letting it go on for 10 years without telling any students because we're all complete idiots. Until this company, USDN, a local San Francisco contractor that created this entire situation, comes in to rescue us from it with unspecified means, which in fact were never specified at all. But anyway, the problem is this went to the IEEE. It went to television news. The CTO, before he presented it to the Board of Trustees, went in and took that San Francisco Chronicle photographer through the lab to take pictures of our labs that were supposedly all infected. And so I normally talk about outsider threats and sometimes insider threats, but now I have a new category of diluted insider threat. So when the high-privileged people on your network are out of their minds, then what do you do? Now, there were considerable reasons to believe this was not true. The simplest one is we had two complete generations of hardware replacement of our desktops in these 10 years. One of the stories in the newspaper that also came from this contractor is that we've been infected for 10 years and we never even noticed. So that's kind of hard to do. And especially when you replace the entire computer. It's not incredibly obvious how it is that the infection survives that. Also, we use antivirus, we use deep freeze, we divide our network with segments, we got a firewall. We have a lot of security measures, far more than most colleges, so it's kind of hard to believe. And there was a professional security audit a few years ago, and my students and I did a less professional security audit as part of a class, and I'm thinking, I really don't believe all of us missed this, but the trick here was the people claiming this would prevent us from seeing the evidence. There was supposedly some report back in November which led to the January disclosure, but we never saw that report at all. It appears that report never existed at all. And we spent the entire rest of the semester dealing with lies and evasions and delays as people kept saying, we've got the report, but you can't have it for this reason or that reason or that reason. And committee meeting after committee meeting, probably best described as lynch mobs. And we finally got a partial report, but it was missing all the appendices, which would include the actual evidence. It just included the claims that you're all infected. And then when this report made a big deal about how this is proprietary and confidential, and the contractor and the CTO tried to tell us it was so confidential that even we couldn't see it. And the vice chancellor said, well, we paid for it. How come we can't see it? And then later on, the CTO published it all in the newspaper anyway. So the secrecy is not entirely clear here. But anyway, that claims that we had, that they found all these viruses. They'd already contacted the FBI, which is mighty strange. Why would the FBI care? So I often, at my beginning security classes, right at the start, I talk about this, and I ask my students this one. So if somebody tells you your machine is, your network is full of viruses, who's your management? Who do you talk to? Upper management, your staff? Tell no one. The FBI or the Chronicle. And ordinary people that have not had any lessons in security at all can immediately see that these are not brilliant solutions to the problem. In fact, the reason you hire security professionals is to keep your college off the front page of the Chronicle. The only time I want to see us on the Chronicle is when Obama's giving us an award for being the best college, not because we're idiots and we let viruses run rampant and did nothing about it, especially when it's not even true. I mean, we get in enough trouble for things we really do around here. Getting in trouble for one we didn't even do is just excessively unjust. So here's part of that report. Showed that we had 1,940 PII-related events, which, now what's going on here is this is network forensics. I still have never been able to find out exactly what they did to create this train wreck, but the technique was to monitor our network traffic and look for connections to certain IP addresses and ports, which came from a secret proprietary list from the contractor he claimed to billed from military and secret law enforcement sources that we couldn't know about, which contained the known addresses of all the command and control servers, and therefore, when they see a connection to a certain port on a certain IP address, that means we're infected and something is stealing data. But there was never any packet capture showing that data actually leaving, and I, like I say, had enormous difficulty believing that this was going on, at least to this extent. And so we screamed, and finally, on April 3rd, we finally got a list of all the so-called infected IP addresses, 4,500 infections out of a total of 10,000 machines. And this is going on, and these are not new viruses either. That's what I thought. Maybe this is it's a data persistent threat that we can't pick up, but no, this was old stuff. Stuff that your antivirus would totally catch. And so we went and did a direct inspection of those machines, and there were no viruses. This was all nonsense right from the start. So anyway, that led to a vote of no confidence in expelling the CTO, which took an awful long time because of the ponderous bureaucracy, but he was eventually shoved off campus. And but another thing that's important to notice here is, then he published a letter in the newspaper explaining how this is not his fault, the viruses are real, we need to engage in breach notification, there's a huge conspiracy, the network administrator is in on it, the vice chancellor is in on it, the chancellor is in on it, the lawyer is in on it, everybody's concerned. Worst of all is this Sam Bowne guy who's just no good all around. And these people are all in a giant conspiracy to prevent everyone from hearing about these dangerous viruses that are all important and constitute a breach. And that is what ties it into my next topic here. See, suppose this were true, and our machines were infected with viruses because we didn't use antivirus, and a student went up there and went and shopped and put in their credit card and bought something. That's not a breach. If I go to Kinko's and use their machine and it's got a virus, it's not a breach of Kinko's data security when I get infected. Use somebody else's machine, use it at your own risk. A breach is if the data we collected in the registration process or the health process, and just in a database, if somebody gets that, that's a breach. Because that's data we collected and we have the obligation to protect it. That's when we failed, and there was never any suggestion that this happened at all. By the way, another fun fact about these viruses is that out of these 4,500, 200 of them were Windows viruses infecting our Unix DNS servers. So, I really never got exactly down to the bottom of what they're doing here, but whatever they're doing, they need to knock it off. They're using some stupid technique with too many false positives, like 99.9% false positives here. Anyway, so let's talk about a real breach. A real breach happens for a variety of reasons, but by far the most common reason is SQL injection. If you go to a website and you have some kind of parameter here, if you put an apostrophe after the parameter, and then you see a SQL syntax error, that's the kiss of death. Here's a company with investment news that had it. Here's another one, CIA, not the CIA I was thinking of, it's a housing association in Florida. But they also have a SQL syntax error here. Here's a Buchanan Bond Exchange financial company with another SQL injection. Now these guys have got serious SQL injections, and because of that, they can get hacked. Here's another one, travel agency. And tomorrow we'll go through quite a bit of this. We'll just set up a database, hack into it, and then protect it. Modify it so it's no longer vulnerable. That's the hands-on workshop tomorrow.
All these websites are still alive, right?
Yes. And I notified them personally, and none of them cared, which is very common, by the way. I have a project for my CISSP students where they notify people of vulnerabilities like this, and when you do it very professionally, you get about a 20% response rate. Anyway, people don't know. Anyway, in one of these data dumps from Team Ghost Shell that dumped all the stolen data, they took to these people and actually dumped out the commands they used to get it. And you see they're using SQL Map, which is the Linux tool, which is considered slightly less wimpy than using Havij, which is what we're going to use, which is the tool. It's so easy, anybody can use it without even knowing what they're doing at all. This is how Anonymous stole the data from PBS. You just put the URL up there and click sort of go, we'll do it in the project, and out comes all the data. You don't really have to know anything about what you're doing if you have a simple kind of vulnerability. So here's what Team Ghost Shell stole in August of last year now. And I thought it was interesting when they dumped stolen data from many companies to look at how people are handling their passwords. Here's their usual raving nonsense about how they're bettering the world by doing this. You can pretty much skip over that. But anyway, here's all the people they hacked into, CIA services, which is that housing development people. And so here's categories of password storage. Here's something so bad I didn't ever thought it could ever happen. Suppose you run a company called Buchanan Bond. Well, not only do you store the passwords in plain text, but they're just all the same, Buchanan Bond. I hadn't thought of that. That's just the name of the company. A lot of them are just the same. Here's another one, a company, Reeves Law Associates, AC Law, FD Law, APL Law, LJ Law, 1, 2, 3. Not only they store it in plain text, And the shortest 4 letters, but most of them are all just the same. Yeah, 1, 2, 3, 4, there you go. Here's Sparkland. The company's name is Sparkland, and the passwords are, of course, Sparkland. Now, you're not supposed to store passwords in plain text, but if they're going to be like that, it hardly matters how you store them. And there's B Forward, is a company that sells auto parts in Japan, and this is the personal identifiable information. Here they've got addresses of people and their names. That's PII. These guys now have a PII breach. And I don't know what happens in Japan, but if this was America, they've now got a bunch of work to do to notify those people who lost their data. Here's some plain text passwords, or another one of these companies. You see they're pretty short and stored in plain text, but at least they're all different. The BUEZ, BUZ, Here's another one. These guys didn't want to get their passwords stolen in the event of a breach, so they encrypted them with base 64, which, and they, in case you're worried, we employ commercially reasonable security measures to protect our data. So don't worry about that. But as you know, base 64 just means you take the bit 6 at a time instead of 8 at a time. It's not encryption at all. It's just obfuscation, and you can reverse that trivially with an online.
So how do you know base 64?
Well, you just look at it, actually. And if, the fact that it ends in equals is a really good tip. Base 64 always has uppercase letters, lowercase letters, 0 through 9, and 2 punctuation marks. One of them's equals. And almost always ends in equals. So it's pretty easy to spot. And then what you do is just go to an online base 64 reverser and see what happens. And it turns into things that look pretty much like reasonable passwords. So anyway, all right, so now what other people will do, which is getting a little better, although it's still almost completely useless, is hash it with MD5 or SHA-1. Now MD5 and SHA-1 are real hash functions, and they take a password, like here's one that was Hiawatha. They turn it into this long binary string, which you write as hexadecimal, and it looks pretty good. The problem is they're easy to calculate fast. They're designed to calculate fast, so you could easily make a huge dictionary of passwords and hashes and run it backwards. And that's the principle of a lot of online crackers, and I was able to crack ones they couldn't crack by just using an online cracker. This is Borg 7R5A. You know, that's not an enormously obvious password. That's not like an English language word or something, but it's able to crack in a few seconds with just a free online tool. Now, of course, if you're a pro, you get a bunch of GPUs and Hashcat, and there's tools that will really do this efficiently, but if you just use these online tools, you're just using the data dumped by earlier generations of people. Yeah.
You're not hashing it, you're just looking at a table?
Yeah.
Like a rainbow table?
Well, yeah, but rainbow tables are actually on the way out. But yeah, mostly you just do the calculations because GPUs are so fast that they can just try a lot of guesses until they find it. Yeah?
You could also rent those fast machines on Amazon?
Yeah. Yeah. You put on E2C, yes. And there's also services like the one Machi Marlify put up that will just do it for you. They'll connect you to a special cluster of machines to crack them. So I mean, you can rent time on them, but even just the free online trackers are good enough to get some of these from these data dumps. So MIT, one of the MIT servers got breached, not the main one, of course, and they actually have a nice form. You can turn in the information about the breach, which is nice. I don't know if they did anything about it, but at least they have the form. And here's their passes. There's their hashes. These are MySQL 323 hashes. There's really only about 6 common types of hashes out there, all of them completely worthless, just to jump to the point. You can crack those in Cane. Cane will take a while. I didn't wait long enough for it to crack these ones, but it will attract MySQL hashes. Here's a SHA-1 hash. And as you can see, the hash is longer than an MD5 hash, which makes it a more secure hash function. What you're trying to do is verify that a file someone downloaded has not been altered, but it doesn't help you at any, if you're hashing passwords, it doesn't do you any good at all. And you can just reverse those online too. Here's another one. I reversed this one online, and it's Ben2469070. Again, you know, not something trivially in a dictionary, and yet even a free online cracker can crack it. So here's MySQL 5 is another type you'll see out there, and WordPress with the $P in it. These are all modern variations of the others. Here's relative space. These look like, I think, SHA-1s. And see, the person that dumped the data was able to figure out Chicken 2 and Marine, but they couldn't figure out the D4 one. But I think I just tried running that through an online cracker, and yep, I got it. The D4 one is Evanet. So if you hash your passwords with any of these systems, you might as well store them in clear text for all practical purposes. I mean, because after they're dumped out, it's only a matter of a few hours before everybody can reverse them with these readily available tools. So here's another data breach where these guys lost the name and addresses from these companies, and that's a real data breach. This is when you have to notify people and such. Yeah?
Sorry, Dennis.
Feel free.
How much difference would it make them to have like a 20-character password? Is that too practical swim?
No, if the password is longer and more complicated, I would think that would slow you down. And I think the only random ones they can get up to now with the best GPUs are about 12 characters. So you'll have a little bit more life that way. That's another issue, of course. Anyway, so let's talk about password hashing. And here's a wonderful article that goes through all the types of password hashes that are out there right now, which is really only about 8 or 9 in common use. And they all work about the same, and they're all completely useless because they're fast. The point of these algorithms is these SHA-1, SHA-512, MD5 were designed to calculate fast, because if you download a 5 gigabyte file and you want to calculate the MD5, you don't want to wait weeks while it calculates it. So you have to use something that calculates really fast. And therefore, it's trivial to crack because you can make a huge dictionary. What you want is something that is slow, and that's what bcrypt does. There's bcrypt, there's another one, PDF or something with a longer name. Both of these just do something like, for example, a Linux logon password on a Ubuntu Linux box or a Mac OS X box just does 5,000 reps of SHA-512. And the only point of doing 5,000 reps is to waste time. There's no way to shortcut that process, so the only way to calculate a hash is to do 5,000 reps. And bcrypt and these others are designed to take 50 milliseconds to calculate a hash. That's your goal. If it takes 50 milliseconds to calculate a hash, the user will not notice any delay. It won't cause any problem in normal use because you only log in once. But it means you can only calculate 200 hashes per second. Something like that. Did I do that wrong? 2,000 hashes per second? Anyway, not that many. If you have an input database of 10 million passwords and you want to hash them, you've got a big problem on your hands, which you wouldn't have with these. So that's the point about password hashes. And I must say, I thought that was my main point, to get to people. I don't know how many people actually oversee databases here. I went to Baythreat, and there was a lot of people there that oversee databases, and now the whole room, only 2 people were using secure hashing. Does anybody know if their company is using secure hashing here? Yeah, nobody knows. Yeah, we're not the right crowd for that. Anyway, yeah.
What is bcrypt? What does it do?
It, I think it just does thousands of reps of MD5 or SHA-1.
So how do you use it? What do you do with it?
It's when you originally have someone create an account, they type in a password, and you run it through bcrypt, and you store the bcrypt in the database. And then when someone logs in, you calculate the bcrypt or whatever they typed in and compare that, which is the same thing you do with all the other ones. So the only thing you've stored is the hash function, and the whole point is, theoretically, you cannot go from the hash function back to the raw data. But in practice, you can, unless you use one of these hash functions that's designed for passwords, because a hash function designed for downloading file verification is completely the opposite of what you want for a hash designed for passwords. But nobody knows this. None of the content management systems do it. It's not generally accepted, although it's been known for 20 or 30 years. It has not made it into the developer's consciousness that you should not be storing passwords hashed in this other way, or in plain text. Like so many security issues, it's the emperor has no clothes. What we're doing is stupid. Everyone knows it's stupid. Nobody cares. Anyway, so that's the password hash stuff I wanted to tell you. Maybe you can pass it on to some programmers that learn these bad techniques. Now I want to show you the new thing, which is IPv6 router advertisements, which I'm going to attempt to demonstrate here. We will see if my pile of equipment will hold together long enough to do it. So the old attack, all the way from 2011, ancient history. Now, if you boot up on a machine and you're connected to a LAN in a world of IP version 4, you ask for an IP, you get an IP with DHCP, there's a couple of verification messages, and that's it. You won't do anything more in this until you reboot that machine under normal conditions. You can do that in IPv6, but that's not what's typically done. What's typically done is router advertisements. You send out these router advertisements and command every machine on your LAN to join the network. And they all have to stop whatever they're doing, configure an address, and join your network, which is not that big a deal unless you send a lot of router advertisements, in which case you can burden those clients. The router advertisement goes out here. It goes to FFO2:1, which is an IPv6 multicast address that goes to all nodes. So for all practical purposes, it's the same thing as what we used to call broadcast, although technically it's a little bit different. And it passes a prefix out there. This means I am the router, this is the route, this is my network prefix. Everybody make up the rest of the other 64 bits somehow and join my network, which is fine, except it turns out that quite a few machines are incredibly inefficient at doing that. For example, Windows. For some reason, which I've never had explained to me, it takes Microsoft Windows 200 milliseconds at 100% CPU to add one address to the adapter. I don't know what it's doing, But if you send 5 of these per second, it pushes the CPU up to 100% and it just stays there. And if you send thousands of them per second, for a couple of minutes, it builds up a huge backlog. And even when you pull out the adapter, disconnect the cable, do anything you like, that machine is at 100% CPU for hours and hours, chewing through that long list of addresses, joining a bunch of networks that don't exist. And I did this in a wireless network on a stage, and I used a USB wireless NIC, and I pulled out the NIC. And the machine stays there frozen. I said, you know, what is it doing? The NIC is gone. It's not adding addresses to this NIC. But it's still busy doing whatever it thinks it needs to do that is tied up for a long time. And that's the attack from a couple of years ago, which would freeze a Windows machine and a BSD machine. I think it was OpenBSD. There's one of them that's super secure, FreeBSD and OpenBSD. I never remember which is which. The one that is proud of being secure, has no IPv6 by default, is therefore immune. The other one is vulnerable. Anyway, so that, yeah, FreeBSD. FreeBSD and Windows are used up by this. Mac and Ubuntu Linux are not affected by that attack. Ubuntu Linux will just configure the first 10 addresses or so and then quit. So there's the new attack, which just came out about a month ago, which is a simple extension. All you do is put more information in each router advertisement. You can put more than one route in the same router advertisement. I'm not sure exactly why, but it is permitted by the protocol. So you send it 17 routes, 17 prefixes, and 18 routes, which means you have to make up 17 addresses for every one of these packets you get, and then you have to make up 18 routes and put them in the routing table for every one of these packets you get, just to give you some busy work to do. And that, of course, burdens the machines quite a bit more heavily. And so the effect is you get a blue screen of death on Windows 8 and Server 2012. Mac OS 10 freezes and dies to where you have to do 2 cycles of shutdown and restart to get it back to normal. Windows Server in 2008 R2 are no longer as vulnerable because of the IPv6 readiness update that came out on, I think, about November 15 of last year. That does not completely protect you from the attack. It causes it, instead of building up a huge queue of stuff that will keep busy for hours, it just freezes totally during the attack, but when the attack stops, it recovers. So that's a partial defense. It slows and sometimes crashes the iPad 3, kills the Microsoft Surface with the blue screen of death over wireless. Ubuntu sails right through as if nothing's happening, no problem at all. So it is possible to survive this stuff and have a correctly functioning IPv6 stack, but none of the other operating systems have figured out how to do it. And I'd like to demonstrate this thing, but since it's going to kill all my machines, I'm going to finish the slides first, although this time I'm actually using a different machine. But anyway, I made a page with a lot of videos about this, showing you killing different machines, which is a pretty good way to do it. My students are having fun making these little videos, 2 or 3 minute videos on YouTube showing this attack killing one device or another. And by the way, it's probably a good point to mention, if you want any of this stuff, it's all on my website, samsclass.info. The PowerPoints are here in this special event, and that page about the router advertisements is just right here. So if you go there, you see we've got, I think we're up to 13 items here, killing the Surface, freezing Android phones, so I contacted Google. Android is vulnerable. MacBook Air, iPads, anyway, lots and lots of machines. We've been developing this attack gradually with time. For a while, it took a $600 switch and a bunch of equipment. It was really hard. Then we figured out how to do it. So let me show you how it works. But first, I'll finish talking about the slides. So if you want to prevent this, you could not use IP version 6. I'm pretty sure that'll save you. You could turn off router discovery. If on Windows machines, there's a netsh command that stops router discovery, and that means it no longer automatically configures addresses. So if you're willing to manually put in addresses, which is probably appropriate for a server, you can just turn this off, and that protects you from the older attack, and I imagine also the newer one, although I haven't tested it. The Cisco solution is use a firewall, block rogue router advertisements. You have RA guard, which means we only have one physical port that's allowed to send router advertisements, and if any other device tries to send them, we throw them away, and that's, of course, going to protect you to a pretty good extent. As you switch with RA guard, you can block it with a firewall also. You can block it with the Windows firewall or any other firewall. You can tell it to just ignore router advertisements or ignore ones that come from the wrong source address, and that gives you some protection, although, of course, your attacker could just spoof the desired source address, but every defense, there's some way to get over it. As I mentioned, Microsoft's IPv6 readiness update provides some protection, so those are reasonable mitigation techniques. One of the projects that we haven't got around to, one of my students wants to do, is try a bunch of antivirus and software firewall products, like McAfee and Norton and stuff, and see if any of them protect you. And if not, they could easily update to protect you, and why not? It's probably quite a pain for Microsoft to fix the bug in their system. They have been known about this for 2 or 3 years, and they haven't seemed to do much yet. But just putting it in the firewall to block an excessive number of RAs would seem like an easy fix. You might be able to embarrass some of those guys into doing it.
So, yeah. Microsoft's virtual switch router guard will protect.
I don't know about it.
Okay.
It'd be interesting to play. By the way, Cisco's RA guard is easily defeated. That Mark Hauser, we've got this. I didn't get any of this, by the way. This all came from Chaos Communication Congress, Mark Hauser in Germany. But he found out all you have to do is split the packets in two pieces with fragmentation in the header, and it'll go right past Cisco's RA guard. So this is true of all security measures at first. I mean, you get used to web application firewalls and everything else. The first thing security measures ever do is block the most direct, exact attack, and the slightest variation will sail right through. It's only later as generations you do something more intelligent. So, but it would be fun to see. So let me see what I can do to set this up here. I'm going to attempt to demonstrate some of this stuff. I've got the Mac target here. And it'll take me a minute to get these things projecting. Let me get my projector going. Here it is, good. All right. And here's my Windows 8 target. It's hopefully still alive. Oh, good. All right. Let me get the video. You say all I do is go in there, okay? And there was another video cable right here. There is. All right. So, this is where I think the CCC confer people will no longer get anything out of this, but yep. All right. Let's see if I can show you that. Actually, yeah, we'll start. I'll just go right to the Windows 8 machine. That's probably the most common. All right. There's no Wi-Fi. There's no Wi-Fi. No, I think there's no Wi-Fi. All right. That thing should be right. Good. All right. So let me show you how this attack works. This is Backtrack Linux, and I don't know why I Shift Control Plus. All right. The tool I'm using is space TH. Okay. THC IPv6. This is the Hacker's Choice IPv6. This is the Chaos Communication Congress in Germany. They make a whole series of the Hacker's Choice tools, which are awesome. This is the IPv6 attack suite. The new version 2 just came out recently. And so it contains some much more fun and powerful attacks, and that's what I'm going to use. Now, first thing I want to do is fake router 6 on ETH0 1 : whoops, got to 1:/64. All right. Now that's advertising one route, and I should be able to see the effect that had on this. However, why am I seeing nothing? Logo P. Duplicate is on. Can you hit project computer or something up there? So I get this to go through? How do I do it? Up here? This thing? Oh, good. Okay. Neat.
I don't know.
Let's see if that does something. Maybe? Okay, let's try to get it. Hit it twice.
There.
Life is great. Okay, here's the glorious Windows 8 machine. And I need to hit start and get CMD, and then do IP config. And as you can see, it has now joined a network called 1: It's made an IPv6 address and a temporary IPv6 address. So let me send a couple more fakes. This, by the way, is what really held me up on this attack. What I'm doing now, this is sending one router advertisement per second. And they're all the same network too, so you wouldn't think it would do any harm, but that is absolutely necessary. Let me do a couple more of those. Fake router 6 ETH1 2: and then, oops, I did something wrong. IP address is it's 0 on this machine. That's right. This is a physical machine. I'm so used to virtual machines. Okay. Fake. There. I have 3 of these should do. ETH space ETH0 3:/64. So now I've got 3. I did something. I did in fact, didn't I? Yes. Okay. Good. All right. So now I got 3 of them, and therefore, if we look at that Windows 8 machine, as you can see, it's now made 1, 2, and 3. So this is, and it's not using up a lot of CPU or anything. We're near 0 here. This is harmless. You must do this. A student told me about this. I did this attack, and we had a whole network set up in the room. We had an attack over here. We had a real router leading out of the room. and it crashed Windows 8. Then I tried it alone, it didn't crash it. Then I tried, we'll get all the other junk out of the way and just have a crossover cable, and it didn't crash it. And he said, you have to have a real router in the network. And I said, that makes no sense. I'm sending 3,000 router advertisements per second. How is one more going to matter? So I ignored him as long as I could, but he was right. And that's why we went to Daythreat to demonstrate this. We carried along all the equipment to set it up with real equipment. But you can simulate it with this, which is why it's getting a little bit easier for me to do this demo. If you have 3 devices pre-configuring normal networks, it makes a difference. I wish I knew why. Here's the attack going to go, and I think we're projecting Windows 8 life is good. Okay, flood, router 26, E0, that should do it. Ooh, that is not going to do any good. You know, it does this sometimes, and I might just be hosed. It does this
over here, too.
It did. Well, I thought the fact that I didn't see enough dots there meant the attack was not going to work. Oh, it worked anyway. Wow. Neat. Okay. Yeah, but the dot usually goes, so that's interesting. I don't know why, but anyway, that's it. That kills Windows 8 completely, and by the way, it's bad for your Mac, too. The Mac dies in a somewhat less dramatic way. But that's what I wanted to show you. And when I did it, and see, this kills Server 2012 also, and when I did it at Baythreat, I asked people, you know, I don't understand. The previous attack, I understood. Each router advertisement means the processor has to do a bunch of work. So a lot of it means it has to do too much work, so it goes to 100%. But why would you get the blue screen of death? And they tell me that this is normal. Any kernel programmers here might be able to help enlighten me. They tell me that common in kernel programming, the kernel operations are not checked to see if they're running outside their bounds. You just go too much of a hurry. So it is typical that if you burden the kernel too much, it will just crash. It's amazing to me. I thought this was a fundamental principle of programming. If you have this much of something before you work, you make sure you're not going off the edge. But apparently they don't in kernel programming. So it is common that this happens. The next question is this exploitable? And I don't know, but people at Baythreat seem to think it might be. If you could control this, like a buffer overflow, and make it crash, maybe you could grab the crash and take over the machine. That would be pretty difficult, but who knows? You can do it on wireless networks. You do it to all these different machines. No, it works. I don't know why this was suddenly so slow. Normally this is screaming across at the rate of 3,000 or 4,000 per second, and that's what kills it. Here I didn't see the dots, but it still killed it. So anyway, that is all I wanted to show you. However, I appear to have a little bit more time here. Let me point you to something else, which is probably even more important. Let me figure out how to get back to this machine, which is this thing. All right. I should be able to project this up on the big one. I came across, see, I've given some talks about denial of service attacks at various conferences, and a guy sent me a tweet on Twitter saying that, why did you ignore the SOC stress attack? You should have included it. Anybody know what SOC stress? It was all that catch me out in 2008. In 2008, there was this thing called SOC stress, which was demonstrated at a conference by a guy who later died before he could write the paper. And the result was, let me see if I can get the projector working here, which is this thing. The idea is it was a fundamental flaw in the TCP/IP stack. And you couldn't patch it, and you couldn't do anything to save yourself from it. Let's see if I'm going to get any joy out of this thing or not. Ah, there we go. Okay. So, I should, if I have 10 minutes, I think I have 10 minutes. I should have enough time to do this.
10 minutes.
Ah, wonderful. If anybody got questions, you can call them out. But now I'll show you this other attack, which is maybe even more important, because it's from 2008. I thought it got patched long ago. It did not get patched. People don't care. They are not going to patch it at all. So let's see if I can get my... Oh! Of course. I just killed my Mac. My Mac's not going to work for a while. Duh. This happens to me a lot. I just hacked myself. I wasn't protecting the Mac, but the Mac was in the network and it got those routing advertisements. So in fact, the Mac cannot even be shut down now normally. All you can do is hold down the power button until it dies completely. And then when you bring it back up, it's still not right because it didn't get to shut down properly. You have to shut it down another time. So anyway, in the meantime, I think what I'll do is I won't attempt to demonstrate the other one. I'll just show you the pictures of it. And that also has the fortuitous effect of putting this network back the way it should be before the next poor speaker comes in here. Tries to get everything done after I've trashed everything in sight. But, yeah.
If you perform this attack on a virtual machine inside, is it going to affect badly the external machine?
Yes, it does. That's why I have to carry so much junk around. You can't use virtual machines very much for this attack unless you protect the host. Now, one thing that would probably work would be to use a Windows host and run the netsh command to turn off router discovery. But I'm not aware of any easy way to immunize the Mac from the attack, so I can't use my Mac-based virtual machines for this kind of stuff. And
Which you haven't set to attack each other inside and no connection to the host system.
I tried that, but there's still an adapter going out to the host. There's a shared adapter like VMnet 8 or 9, and it's configuring those addresses. So I think it will still go down, but I'm not sure. And yes, by the way, quite a few of these attacks will kill the host from inside VMware. It's a fairly common thing. Anyway, so the other thing I wanted to show you was the SOC stress attack, which I just got working a couple days ago, and right now it's only in the news. I'm going to make a real page about it and probably start making videos about it, because this is probably even more important. But SOC stress, okay. A hacker contacted me and told me he's actually been taking down sites with this tool. And I said, you've got to be kidding, that tool is from 2008. And in 2009 or so I heard about it. I tried to find the source code and I couldn't find it. And then I found a claim on Wikipedia that said it will kill the machine totally like that IP version 6 attack. And I said, wow, that's great. So I sent a bunch from Windows 8 and it didn't die, and I said, this thing is junk. But then I said, read it more carefully. There's different versions of this tool. Now the way this works is really simple. You send a SYN, and you get a SYN ACK back to connect to a TCP socket. You send an ACK, then you send another packet with a window size of 0, which means, okay, you can give me the data, but you have to give it to me 0 bytes at a time. Now, I do not understand why people think this is okay, but it is allowed by the protocol. Therefore, the source is sort of stymied now. It's trying to send you something, but it can't get anywhere because it keeps sending 0. It's waiting for you to increase that window size to something bigger than 0. So this is a way to tie up the line at layer 4. And if you send those things, it doesn't take very many to kill the source at all. So what I did here was I put up a Linux machine running Apache, and I just, by the way, if you send out unexpected SYNs and crazy acts and stuff, you have to block the kernel from acting. The kernel will reset these. The kernel of your operating system will say, wait a minute, whoever's trying to open a socket around here should not be sending out raw SYNs. You should be requesting me to open a socket, and I will do it my way. So I'll just send a reset and cancel all these weird packets that some moron is sending out on my machine. So you have to block that, which you can block on the firewall. I just configured this thing to drop all reset packets, which is a sloppy, simple way to do it. Then you can use SOC stress and send packets here, attacking this. And after you send only a couple thousand of them, which is really only a matter of 5 or 10 seconds, you've used up all incoming lines. This is like the slow Morris attack. It does this at layer 7. But this is doing it at layer 4, so it'll affect anything that uses TCP, and so it does. Routers, every possible operating system, everybody else. And Microsoft found some related vulnerability where you could actually take over the machine, and they patched that in 2009. But they didn't patch the fundamental problem here, and they're still vulnerable. And another thing about it is, if you do it this way, it frees up one process. But if you simulate a bunch of different source addresses, which you can do with the tool they give you, or use a botnet or something where you have 100 or 200 different source addresses, you can kill the server completely. And what the black hat that tells me about this told me is he brought, 3 days ago, some site offended him in Palestine, so he brought him down in 10 minutes of a flood of this, and they're still down 3 days later. Because it not only crashes your machine, people say it can render your machine unbootable. And everybody has known about it since 2008, and nobody has done anything about it, as far as I can tell. I thought it's ridiculous how many vulnerabilities this bad are still sitting around since 2008, but I think everybody thinks it's somebody else's problem. They think it's a fundamental problem in the TCP protocol. There are many variations to the attack. And anyway, I'll be making some videos about that. That'll be the next fun thing to play with. Because this is even more scary than the router advertisement flood. See, the main reason people laugh off the router advertisement flood is it only works on the local area network. You can't do it to a remote host over the internet. But you can do this to a remote host over the internet. And I know at least one black hat that does it all the time and has been doing it for 5 years, taking down people right and left. So my first motion is going to be to find out if Cloudflare will stop it. If they don't, I'll get Cloudflare to please stop it, because they could. I'm glad to see it's working. I've heard all these extreme claims about it, but I couldn't get it to work. Now I've got it working. There's different versions of it. And apparently this guy is now telling me I'm a wimp for using backtrack. I've got to use proper Slackware if I want to do these attacks, and how kind of idiot am I for not using Slackware, which you get a lot of that. So maybe I'll have to put this on Slackware. Yeah.
What is the setup for this attack?
Nothing. You just have to have a network connection to the target. It has to be a listening TCP port of any kind, and you just start the tool and you type in the IP address you're attacking. And there are more complicated versions that will also send a connection and then some kind of request, and then lower the window size down to 0 or even to another number like 4 or 8, which still has the same effect because it takes forever for it to communicate that way.
Which machine initiates the connection?
This one. So you're just running a server, serving clients, and one of those clients is running this tool. They send in a SYN that looks normal. You send out a SYN ACK, they send an ACK, but the ACK has a small window size. So it seems to me like you could configure an IP tables rule to reject all window sizes below a certain number. How often does a real client have you do
machine on the left, is it a web server?
Yeah.
That you are running?
That's what I used in this case. Although supposedly it'll work for any TCP service. When I attacked Windows, I tried a 445 file share. And what I didn't do was then test to see if file sharing is still available, which is what I should be doing. Apparently, I was probably freezing a file sharing. I expected to kill the whole OS, and you don't get that by attacking for just a few minutes from one IP address. But you can apparently kill the whole OS. That would be the next fun thing to try. But even at this, it's bad. This way you can take down websites. I thought the slow lowest attack was the end of the world. The slow lowest attack is at layer 7, where you've sent an incomplete HTTP GET. You never finish it, so the server has an incoming line occupied by a partial request coming in, and it's waiting for the rest of it, and it takes 200 seconds by default for Apache to give up on that. So they're just sending 1 packet per second. You can freeze the server so it doesn't deliver any pages to anybody. I thought that was really bad, and in fact, people did put up lots of security rules to stop it and such. But as far as I can tell, nobody's done anything about this, and the guy tells me he's taken on sites right and left. It is not patched at all. And at very least, there should be some kind of thing you put in your switch or something in your firewall about this. It doesn't seem that hard. You can make a firewall rule that just looks for the size of window and doesn't accept any window sizes that are too small to make any sense. I don't know why the protocol even allows small window sizes. How often do you really want something 4 bytes at a time?
Isn't it for congestion control?
Yeah, but how much congestion? I mean, if you got that much congestion, the user's never going to see your page anyway. I'm going to send you my page 4 bytes at a time and pretend you're still going to.
No, but
yeah, I did for
you
congestion.
read back.
Yeah.
The reason that you consider window size of 0 is for congestion control.
Just to tell it to wait.
Yeah, to essentially back off.
Well, then it should just cancel connections and not consume any more resources after it gets to 0.
But then you'd have to reestablish the connection.
That's right. I think I'd be quite content doing that on my server. It probably would not violate, it probably would not strictly obey the RFCs anymore, but it would probably really continue to deliver service to any real devices out there that are actually trying to get it.
Yeah, but so I think you're talking about then versus now.
Of course, I think that's what happened. You know, we got this is like many of these things is a legacy thing that might have made sense 20 years ago,
Right.
but now it's just a hole to drive a truck through.